Good morning one and all. Today we will going to discuss about the network theorems. The first theorem is the Thevenin's theorem. First we will going to discuss about the statement of the network theorems. A linear network consisting of number of voltage source and its resistance can be replaced by an equivalent network having a single voltage source called as the Thevenin's voltage and the single resistance which is called as the Thevenin's resistance RTH. Thevenin's voltage is the VTH and the Thevenin's resistance is the RTH. From this figure we have to be understand that here instead of the E you use their voltage source V also, no problem. Here is the voltage source E should be provided. The resistance R1, R2, R3 are connected in R2 and R3 are connected in parallel in series with the R1, and the load resistance is connected between the two nodes, that is the node A and node B. Then we move forward. This circuit we have converted into the Thevenin's equivalent circuit. The Thevenin's equivalent circuit, the whole circuit is converted into the Thevenin's voltage VTH in series with the RTH, and this load will be connected across the node A and B. Consider the network circuit as shown in figure. Let E be the EMF or the voltage is able to applied, source voltage is able to applied across this circuit, which is called as the EMF of the cell having the internal resistance R which is equal to 0, and the load resistance will be connected between the terminal A and B where R is replaced. Then we have to be find out its, the first step is that you have to be remove this load resistance RL between the node A and B. First it will be removed it, and then you have to be look in the right hand side towards this circuit. For this case first it will be removed it, and you have to be find out the voltage drop across the R2 which is nothing but the VTH, and in series with the RTH means to find out its Thevenin's equivalent resistance while this voltage source is replaced by the short circuit. Then what we do for the next, see here the load resistance. First load resistance is removed. Here the load resistance, and this load resistance is removed, and the current I in the circuit. If the load resistance is removed, then whatever the current I in the circuit, the current will be flowing towards the here. Here is the open circuit, that's why the current is a flow from R1, R2 respectively. Therefore I which is equal to the total voltage E or total EMF E upon R1 plus R2, because this is the open circuit and current is would not able to flow through the resistance R3. Hence the voltage drop across the AB, the voltage drop across the AB is nothing but the Thevenin's equivalent voltage VTH. Therefore VTH which is equal to I into R2, and according to the current divider rule, here is the current is not divided, but here R2 upon R1 plus R2, here is the resistance should be equivalent resistance we have to be calculated here. That's why the voltage drop across the R2 upon the total resistance we have calculated. Therefore VTH which is equal to I into R2 which is equal to VTH E into R2 upon R1 plus R2 which is nothing but the VTH. Then we find out the next parameter, that is the RTH. Here is the RTH. How to find out RTH? Whatever the voltage source is given here, that voltage source in this voltage source E is replaced by the short circuit. Suppose instead of the voltage source E, the current source is given, then it is acting as the open circuit. But here in the given example, here the EMF E is given or voltage source is given. That's why while calculating the RTH, the voltage source is replaced by the short circuit. Therefore RTH is calculated here, the voltage source is replaced by the short circuit, and we assume that, let us assume that the current is a flow from A to the B. Once the current is coming from A, for this node the current is divided and which is flowing through the R1 and R2. That's why R3 plus R1 in parallel with R2, and throughout the process the load resistance RL is removed and which is connected at the final proof. The load resistance RL is removed and the cell is disconnected and the wires are short as shown in figure here, and the effective resistance across the AB which is equal to the Thevenin's resistance. Then this RTH is calculated, this RTH which is equal to R3 plus R1 in parallel with R2, means R3 plus R1 R2 upon R1 plus R2. R1 is parallel to the R2 and this combination in series with the R3, means R3 plus R1 in parallel with R2, as we told earlier. If the cell is the internal resistance R, if here the value of the internal resistance R is for ideal case R which is equal to 0, but suppose we have considered, then we have to be adding here PTH which is equal to PTH which is equal to E R2 R1 plus R2 plus R, and RTH which is equal to R3 plus R1 plus R2 upon R1 plus R plus R2, means we have calculated the Thevenin's equivalent resistance RTH. Then we move towards the proof of the Thevenin's theorem. In case of the proof of the Thevenin's theorem, consider a network is as shown in figure here. Here is the electric field E which is to be given. Instead of the E, you use here voltage source V. For this voltage source, the total current is flowing through the circuit is I, and from this node the current is divided and I dash current is able to flow through this circuit. Here is the R1, R2, R3, these three resistances available, and here R1 and in between the A and B the load resistance RL is connected. Then from this circuit we have to be converted here the VTH, means Thevenin's equivalent voltage VTH in series with the RTH, and in between the node A and B the load resistance RL is connected, means this is the given network, and from this network we have to be converted in a Thevenin's equivalent circuit VTH. The effective resistance of the network, the R3 and RL, this R3 and RL in series, and this combination is parallel to the R2 and turns in series with the R1, means effective resistance we have to be calculated with the help of this example here. The R1, for here R1, the current is flowing from the total source voltage. From this source voltage the current I1 is flowing through this circuit, and here is the current is divided, and from this current here R2 and this R3 in series with the RL, means the R3 and RL are connected in series fashion. That's why the effective resistance which is equal to R1 plus R2 into R3 plus RL upon R2 plus R3 plus RL, this will be given to the equation number 1. Then the current I flowing through the circuit, this whole circuit is converted into the equivalent circuit, that is the I which is equal to E upon the effective resistance, and that effective resistance should be given here. That's why the current I which is equal to here E upon R effective which is equal to E upon R1 plus R2 inside the bracket R3 plus RL upon R2 plus R3 plus RL. Therefore I which is equal to E R2 plus R3 plus RL upon R1 R2 plus R1 R3 plus R1 RL plus R2 R3 and R2 RL. Take the cross multiplication and that term is going from denominator to numerator. Then current flowing through the load resistance, from this figure the current flowing through the load resistance is I dash, and for this I dash according to the current divider rule, the opposite resistance upon the total resistance into the total current is flowing through this circuit. Hence we have to be find out here the current flowing through the load resistance which is equal to I dash, which is equal to opposite resistance is the R2 upon the total resistance R2 plus R3 plus RL into the total current I, and the total current I is given in the equation number 2. Therefore substituting the value for I from equation number 2 to the 3. Therefore I dash which is equal to this 2 to the 3. Therefore I dash which is equal to E into R2 plus R3 plus RL into R2 upon R2 plus R3 plus RL into this equation R1 R2 plus R1 R3 plus R1 RL plus R2 R3 plus R2 RL. Therefore this equation here R2 R3 plus RL, R2 plus R3 plus RL in numerator and R2 plus R3 plus RL in denominator gets cancelled, and the equation is I dash which is equal to E into R2 upon R1 plus R2 plus R1 R3 plus R1 RL plus R2 R3 plus R2 RL in the equation number 4. Then from the Thevenin's equivalent voltage we have calculated the Thevenin's voltage VTH which is equal to E into R2 upon R1 plus R2 in equation number 5. This is the equation number 5. Then Thevenin's resistance we have calculated RTH which is equal to R3 plus R1 R2 upon R1 plus R2 in equation number 6. Consider the equivalent circuit. The I double dash is the equivalent circuit should be given I double dash which is equal to VTH upon RTH plus RL, means from this equation I double dash which is equal to RTH upon RTH plus RL, simply Ohm's law use here. And from this circuit I double dash is provided in substituting the VTH and RTH from equation number 5 and 6 in equation number 7. Means this 5 and 6 in the equation number 7 means VTH which is equal to E into R2 upon R1 plus R2, and here equation number 6 the RTH is provided R3 plus R1 R2 upon R1 plus R2. We have substituted equation number 5 and 6 in equation number 7. Therefore after substituting the equation number 7, the I double dash which is equal to ER2 upon R1 plus R2 plus 1 upon R3 plus R1 R2 upon R1 plus R2 plus RL. Then rearranging the equation such a way that there is a ER2 upon R1 R2, this R1 R2 into R3 R1, R3 R1 plus R3 R2. Again we have take here cross multiplication plus R1 R2. This is the R1 R2, then RL, here is the RL is given R1 RL plus R2 RL. Then I double dash is converted such a way that E of R2 means this will be gets cancelled out, this and this R1 R2 in a denominator numerator part and the denominator part, this R1 plus R2 and R1 plus R2 gets cancelled. Therefore the equation the I double dash which is equal to ER2 upon R1 R2 plus R1 R3 plus R1 RL and R2 R3 plus R2 RL. This is the equation number 8. Then from equation number 4, here is the equation number 4, and the equation number 8, here is the equation number 8. It is observed that the I dash which is equal to I double dash, means for here the Thevenin's theorem is verified. I hope that this video would you like it to understand what is the basic Thevenin's theorem and proof. Thank you very much.